I've learned this word from philosophers, a perspectival point of view with regard to the direction of time. Okay. So here's just a short history of time symmetry, of team time symmetry versus team time asymmetry in quantum theory. So first of all, Schrödinger in 1926 gave time symmetry the lead because his equation is time symmetric. And that was good because previous physics had been time symmetric, so this seemed to make sense. But then von Neumann came along, and we had the von Neumann projection, or collapse. And it looks like this is time asymmetric because the wave function evolves and it gets hit, and it collapses, and then it starts evolving again. It's clearly a time asymmetric notion. Then in 1964, Aharonov, Bergman, and Leibowitz showed how you could recover time symmetry. And they have a pre- and post-selected view of quantum theory, this enables you to return to a time symmetric point of view. So you have some initial state that you pre-select in, some final state you post-select in, and then you look at the probabilities for measurements in the middle, and the formula for that is time symmetric. And so it looked like time symmetry was winning again. But then, so all of these preceding things I mentioned, Schrödinger, von Neumann, ABL, referred to the pure state formulation of quantum theory. And if you're like me, you'll believe that the real state is the mixed state. The mixed states are much deeper than pure states. And if you start to look at quantum theory for mixed states, where you have operational formulations of quantum theory that work for mixed states, then there is this thing called the Pavia causality condition, which says that the deterministic effect is unique. What it really says is that probabilities for the past don't depend on choices in the future. And this condition, it turns out to be the essential condition in quantum theory. And it's a time asymmetric condition. So you go back, team asymmetry is winning again. And then recently, various people, most of whom are here, showed how to go back to a time symmetric point of view. So Ognyan, Oreshkov, who will speak, I think, after me, and Surf, Andrea Di Biagio, Donna and Ravelli, two of whom are here, and then in my own work, so a way to recover time symmetry. And actually, in these works, there seems to be two different approaches in the sense that Ognyan's work looks like it takes a different approach from the work that of Di Biagio and myself. So my work is very much related to this work that Andrea and Carlo did. Okay, well, there are time asymmetric clouds on the horizon. I mean, in some sense, my wife keeps reminding me that obviously nature is really time asymmetric. You just have to look and see that that's true. Every time you drop an egg, or you see that nature appears to be time asymmetric, really. And so it may be that time asymmetry will win. Or perhaps we can take a different point of view, a sort of perspectival point of view, what I call conditional frames of reference, where we can show that the point of view you take depends in some sense on what conditional frame of reference you're in. This will be a frame of reference notion suited to this situation, not the normal sort of Galilean or Einsteinian point of view. So perhaps that's the way out. Okay, so standard operational quantum theory is time asymmetric. This is familiar to many people in the audience. The usual conditions that are given on operations are that the operations are completely positive. That turns out to be a time symmetric constraint, and also that they are trace non-increasing. And this is a time asymmetric constraint. So I've drawn diagrams for these conditions. This relates to the Pavia causality condition, relates to the fact that you can't send information backwards in time. Okay, and also there's another place where you can see time asymmetry in the standard operational framework is that you have the Steinspring dilation. So any operation in quantum theory can be dilated, so you can regard it as a unitary operation on some ancilla. This is the A, which is prepared in a pure state, and your original system. And then you trace out, this is the I, looking at the screen. The I, you trace out over the I. And so that is a way of forming any general operation on mixed states. It doesn't have to be unitary. You can always dilate so that you get a unitary operation on the original system and some ancilla. And it's a time asymmetric notion. Okay, so how do we make all this time symmetric? The idea is that if you look at the usual framework, it's kind of missing something. The usual framework has settings. Settings are like the choice of knobs or something, and those are available both before and afterwards. And you have outcomes like lights that flash, detectors that click. These are your outcomes. And the idea is to add an extra thing, which I call incomes. So incomes are information that you send into your operation, then it might get eaten up by your operation. Okay. So an example would be to send, in quantum theory, an example would be to send one state from a basis set of states. Okay, and then that state could get eaten up. And this is kind of the time reverse of an outcome. So incomes are available before, but not necessarily after. Outcomes are available after, but not necessarily before. And these are classical things. So this is just a bit more notation. So we use, we say that the outcomes take values given by x, outcomes and incomes take values given by x and y equal to 1, 2, 3, etc. Okay. Now what you can do is you can wire together these operations in the form of a circuit. Okay. And then if you want to take a time symmetric approach, you can calculate the joint probability over all these outcomes and incomes. So normally, you would condition on incomes, and you would look at the probability of outcomes. That would be a time forward point of view. But here we take a time symmetric point of view. We want to look at the joint probability of outcomes and incomes. And now you want to do a bit more than that. You want it to be the case that when you calculate these joint probabilities, you get the same answer whether you do that forwards in time or backwards in time. And it turns out that if you want to be able to do that, then these boxes, which I could point, anyway, these boxes, you see the boxes with the E and the F and the G, those boxes indicate distributions over incomes, and the boxes with the Q and the R and the S, those indicate, if you think backwards in time, distributions over the outcomes. It turns out that all those boxes have to correspond to the flat distribution. They have to be a flat distribution over those incomes and outcomes. Okay. So if we want to have time symmetry in this circuit framework, so we get the same, then given certain assumptions, there are some assumptions in the background here, you need to have this time symmetry. Once you do this, you can now revisit the conditions on operations. Remember, previously we said that operations were completely positive and trace non-increasing. Now we get some new conditions. I'm not going to go into details, but these conditions are time symmetric. We get time symmetric conditions on operations. So this gives you a time symmetric way of thinking about quantum theory. And we also get a time symmetric dilation theorem. So here, a general operation can now be expanded in terms of a unitary and the various elements. And the key thing here is that this is a time symmetric dilation. Okay. So that was a time symmetric point of view where we looked at joint probabilities over incomes and outcomes. But we might be interested in a forward point of view, a forward in time point of view. like I said. And in that case, we calculate the conditional probabilities. We calculate conditional probabilities of outcomes given incomes, or something like this. Okay, so this box with the sort of angle in it indicates conditioning on what's inside the box. Okay. And we can go backwards and forwards between the conditional point of view, so between the time forward point of view and the time symmetric point of view. What we can do is, you see, on this side here, we have just these joint probabilities, and we can use this standard formula from probability theory to calculate conditional probabilities. Okay. Now, it turns out one of the special things that follows from the double causality principle I gave earlier is that this denominator is equal to 1 over nx, ny, nz. Okay, it's not completely obvious, but it's easy to prove. And so that means you can write this. Okay, so here we have the conditional probability is given by this thing here. And here we've gone into, at the bottom, you see, I've taken the factors n, and I've put them in here. And this is a transformation from the time symmetric frame of reference to a time forward frame of reference. You can also do the same thing. You can go to the backwards frame of reference. You can transform to a backwards frame of reference. And you can have the time symmetric frame of reference. So you have all these different sort of conditional frames of reference as a way of thinking about this circuit experiment. You can also expand this, and you can sort of have continuous possibilities that extrapolate between the time forward, the time backwards, and the time symmetric. I won't talk about that. And so we come to this conclusion. Quantum theory admits multiple conditional frames of reference. The question is, why is the conditional frame of reference we naturally use the time forward one? Well, in simple terms, it's because we remember the future, but not the past. And why, we remember stuff like, for example, yesterday, for those of us that were here, we remember celebrating Lee's birthday. Happy belated birthday, by the way, Lee. And if we think we can conjure up that memory, and we can't do the same thing for the future. So why is that? Is it because we have special initial conditions of the universe? So I don't really fully understand this, so I'm just going to ask various questions. Is it because the universe has special initial conditions? I have problems with that answer, but it could be true. Is it something to do with the way that we, as humans, are constituted? Is it the way our brains form memories? Could you imagine being constituted in a different way where you would live a time symmetric or a time backwards life? Is it because there is a special role for consciousness? When we think about, it's weird, if you think about celebrating Lee's birthday yesterday, you can recall that memory, and what you're doing is looking at some state in your brain and attributing meaning to it. You're not directly observing the birthday celebrations yesterday. You're looking at memories, attributing meaning to that, and it seems that maybe consciousness is playing a role in that. Or is it something to do with the beliefs that we have? So one point in favor of this is that the causality constraints that we have are constraints on probabilities. And according to some interpretations on probabilities, they are degrees of belief. So we have these beliefs about causality which are encoded in probabilities. So maybe that's a way to think about that. I've been puzzling over this for a number of months now, and I really don't fully feel at ease with this. So these will be some questions for the discussion. And that's 15 minutes. You can help me get asked it.
Well, thank you very much, and thank you to the organizers for conceiving and putting together such an exciting event. So I think everyone who is truly interested in the foundations of physics must be bothered a little bit by the special link between quantum theory, at least in its standard formulation, and time. Because as you know, the basic rules of quantum theory, they presume a time axis because they're formulated in terms of transformations that happen in time, and they prescribe probabilities for the occurrence of such transformations or events. And what is more, it appears that these probabilistic rules are time asymmetric, the Born rule in particular, and if you try to apply it backwards, it somehow does not quite seem to make complete sense. And I think it is important to try to understand the origin of this, both because it is clearly a very important foundational problem. All the theories we know, the classical ones at least, or the closed system evolution, the Schrödinger equation, they are all time symmetric. And here there appears to be some issue with time symmetry. And in this very short talk, I want to basically convey to you just three main messages. The first one is that I would like to argue that the validity of the Born rule under time reversal would actually be inconsistent with the possibility of having faithful memories of the past if you apply the rules of quantum theory, that is the basic ones, to at every scale, in particular to systems that serve as memories, like observers. And then I would like to argue that the arrows of memory and causality could be understood, it could be derived from specific past-future boundary conditions. This is basically linked to this two-time state vector formalism, or a version of that. Actually, I want to highlight the fact that an initial condition in this framework does not seem to suffice to derive the memory arrow. And finally, I mean, an important thing that I want to say is, in my view, is that time symmetry, this is well known, it could be saved by a certain generalization of the Born rule, basically the two-state vector formalism. But what is important, I would like to stress, is that if you take that formalism seriously, analyze its implications, it implies in particular more general possibilities that are afforded by the standard formulation of quantum theory, and I think this could be important for physics in principle. So the problem with time symmetry in quantum mechanics was nicely kind of identified and formalized by Watanabe in the middle of last century, and essentially can be summarized as follows. You can imagine just a sequence of two, let's say, von Neumann projective measurements. Let's say one is performed by Alice, the other by Bob, and you ask what are the probabilities for Bob to obtain outcome J, given that Alice observes outcome I. This is the problem of prediction, and this, as we all know, is given by the Born rule. The reverse problem of retrodiction is to predict the outcome of Alice given the outcome of Bob. But for this, I mean, if you think about it, you can use bias and inference to solve that, but the answer in general depends on the initial state on which Alice applies the measurement. Of course, if you assume that the initial state is maximally mixed, you recover the analogous rule. But it appears that this is a very special case, and somehow there seems to be this unconditional validity forward in time of the Born rule. And somehow, when you think about it backwards, you seem to need to postulate a very particular case and does not seem to apply unconditionally in the same way. So does this mean that the Born rule does not hold backwards in time? Well, one needs to think more carefully about that, but I think what you may try to say is, okay, forward in time, the Born rule holds only conditionally on the preparation and the measurement, and it's unconditional on anything that might happen in the future or anything that might happen elsewhere. So perhaps it also holds in the same exact sense backward in time, but it's just that we somehow, when we analyze this experiment, we condition on certain variables that we're not supposed to condition on, and that's why it appears that somehow it is violated. And I would like to, and this is my understanding of this recent paper by Di Biagio, Donna, and Rovelli, and just also mention the work of Hardy, which follows the same approaches, although it's not entirely clear to me, but we heard just now precisely his view on how that comes about and how it can be justified. So that's potentially, there are some differences. But I would like to argue now that this actually approach seems to lead to inconsistencies if you want to model the process of memory consistently in this framework. So essentially, just before I formulate the main argument, I just want to remind everybody just some elementary concepts in the context of Bayesian inference. There is the concept of a prior distribution. This is a distribution that an agent who makes inference based on evidence needs to assume in order to make inference and update their probabilities, which are assignments of their beliefs about the likelihood of different types of events. For instance, you can imagine a universe like that with some random variables, which might be the outcomes of quantum measurements, and maybe an agent takes as a prior a specific joint distribution, and then conditionally on observing certain of these variables, they can update and they can derive conditional probabilities. I think this is important to keep this picture in mind because I think the problem boils down to essentially understanding the analysis of the previous experiment in these terms. So essentially, like I said, the Born rule forward in time prescribes probability conditionally only on the preparation and the measurements. So the question is, could the same hold backward in time? And it's like a no-go theorem, this claim, although it's not formulated particularly rigorously. Essentially is the following: assuming that reading of memory corresponds to a local measurement on a memory register, this would be incompatible with the possibility of having memories, non-trivial memories of the past. And the proof is extremely simple. It's just that if you really imagine that, there is this prior distribution out of which you start, which in this case would be translated to a prior state, let's say, of the universe. At any moment of time, you must believe that the prior state should be maximally mixed, because it is indeed, if the Born rule holds universally backward in time, it must always be assumed that the prior state that comes from the past is maximally mixed. And so it must be then the case that if a local agent or observes a local memory register, you should make the inference and kind of be able, in principle, to build out a whole inference or consistently about the whole world or any memory, what happened in the past or something that might be happening elsewhere, just based upon such a memory measurement or such a reading of memory, maybe in your brain or something like that. And so, but the maximally mixed state is maximally uncorrelated. It's uncorrelated on any factorization of the Hilbert space. So really, the memory register could not possibly be correlated, and therefore you cannot possibly infer anything about other systems at the same time, if this is your prior state. And so, but this also implies that you could not also infer anything about past outcomes of von Neumann measurements, because as you know, a von Neumann, like a standard projective measurement, changes the state of the system on which it is applied, and therefore the outcome of such a measurement should be correlated with the state immediately after the measurement or its evolved version into the future. And therefore, if you could know consistently the outcome of a past measurement, it means that you should also be, your knowledge, or which is based upon the present reading of memory, must be correlated also with something out there. And that's a contradiction with what we assumed. So that's essentially the argument. And on the other hand, it is well known that if you assume other than the maximally mixed state in the past, it is perfectly possible to model the workings of memory consistently. This is well established. And what I find particularly interesting here myself is that somehow here, the assumption, this boundary condition, if you like, this past state, which somehow it's something that's not provided by the theory, but you might ask, does it have, what is its ontic status? Does it represent some reality, or is it maybe our assumption? And what I find interesting here is that this assumption of non-maximally mixed prior state encodes this belief that actually we have memories. So in order to be consistent, we must actually believe, we must assume a state that is not maximally mixed. And this belief that we have memories is what one may call a foundational belief, because if you think about it, even philosophically, it's hard to convince yourself. You cannot deduce from inference, depends on the assumptions, but just in principle, it is possible that your memories are not faithful. Therefore, this is one of these foundational beliefs that we hold. And I find it very nice that somehow it corresponds to this specific assumption in quantum theory. Okay, so what about time symmetry then? Can we have a time symmetric theory? Well, yes, as it was pointed out already by Watanabe and then Aharonov, Bergman, and Lebowitz, you can just take the rule that holds backward in time, and this is the two-state vector formalism. You can just, for instance, postulate here that we should define the probabilities based on states in the past and in the future of the measurement, and you obtain this formula. In a mixed state version, it looks something like that. And then, of course, you recover the Born rule in the cases where you have the maximally mixed state in the future or in the past, the retrodictive Born rule. Okay, and actually in this paper, we have developed a version of that more careful operational language, the language of states, effects, and transformations. And one of the implications we analyze there is the fact that you could have more general types of dynamics a priori within such a theory, as well as more general representations of symmetries. So now, finally, how can we understand actually the arrow of time? Well, here is a proposal. Basically, the arrow of time in quantum mechanics boils down to this fact that the Born rule holds unconditionally forward in time, but does not appear to hold in the same sense backward in time. And as we argue in this paper with Nicolas Serre, essentially there is a way to derive that fact by assuming a certain kind of global circuit for the universe. You assume that everything can be always purified into unitary dynamics by moving the outcomes of measurements to kind of outside of the Heisenberg cut, and by following this consistently, you end up with a circuit like this for your toy universe. And there is these boundary conditions that you need in order for this circuit to prescribe probabilities, which basically translate to something like a preparation in the past and a measurement in the future. And it is the claim that the special form of the measurement in the future, where the operators sum up to the identity matrix, is what kind of guarantees that we cannot actually know the outcomes of future operations. We may know the operations that would be applied, but not their outcomes, unless they're trivial. And vice versa, you need a non-maximally mixed operator in the past, which in order for memory to be possible. So how can we account for memory? Well, I mean, I already said it. Essentially, memories, at least our memories, seem to correspond to classical observations that don't disturb the system much. So these correspond more or less to von Neumann repeated measurements. And like I said, you know, in this type of universe, these boundary conditions imply that you could remember the outcomes of such measurements in the past, but you could not remember those in the future. So I think this is one way of arguing for the memory arrow, which follows solely from this quantum picture without any thermodynamic considerations explicitly involved. And what about causality? Well, the thing is, we have now various theories of causality have been developed, but causality, kind of in the fundamental level, for instance, in these papers by John Mark Allen et al., and subsequently developed by others, the fundamental idea is that causality is about influence through unitary channels. And this, you can see that this notion of influences, they are time symmetric. So what is really this idea that we have about causality? Why do we say that we can influence the future? We cannot influence the past. So let's look at a little circuit about a situation that we would normally interpret as depicting influence into the future. So you have, let's say, a circuit like that, some kind of preparation. Alice performs something, Bob observes something else. I mean, in principle, any such circuit, and we'll say there is influence from Alice to Bob if the outcomes of Bob depends on the outcomes in Alice's lab. But the exact same circuit could exist backward in time. And very often, even no post-selection is necessary. There are many of these circuits in which, when you have maximally mixed states or unital operations, that even without post-selection could exist backwards in time. Or so you may ask, okay, if such a circuit could, the analogous time reverse version could exist, why don't we think that we can influence the past? And I think if you think about it, at least this is the conclusion I arrived to, is that really the notion of cause and effect is given by the memory arrow. We say that the cause precedes the effect because it captures this intuition that we all have, that when the cause happens, the effect has not happened yet. And this, if you go back to the picture here, Alice does not remember, she cannot remember at this point the outcomes of Bob, whereas Bob can, in principle, have memory of the outcomes of Alice. So this is the difference really between these situations. Here, Alice, which would be the cause, actually she does not remember she can remember the effect, whereas Bob, who's supposed to have access to the effect, has no memory of the cause in principle. So the proposal here is that really the causality arrow is aligned with the memory just by definition, because at the time of the effect, we could remember the cause. That's the principle, what distinguishes causes from effects. Otherwise, the fundamental notion is just time symmetric. And what about the thermodynamic arrow, you might ask? There have been many arguments put forward that actually memory and all of that can be derived from thermodynamics. Well, I leave that for the discussion. And finally, I would just like to mention that the time symmetric version that I mentioned naturally lends itself to an extension to a time oblivious formulation of quantum theory, which treats time and space essentially on the same footing with the same types of rules. Here is a discrete version that we have developed, but that's pretty much kind of another reincarnation of the general boundary approach that's been advocated by Robert Oeckel. And with this, I'm going to stop. Here is a little summary. Basically, like I said, assuming the Born rule holds unconditionally, back in time would be inconsistent with the possibility of having faithful memories. There are, of course, assumptions in this no-go theorem. Time symmetry could be saved by adopting a more general version of quantum mechanics, which is about experiments defined by pre and post selection. I didn't get into the details about this theory, but you can look it up or we can discuss later. And then the unconditional validity of the Born rule forward in time can be understood as a consequence of the special form of the future boundary condition, whereas the past and future boundary conditions being different, it can be argued to imply the memory arrow of time and also the causality arrow. Now, finally, this more general formulation allows interesting new possibilities that, such as more general symmetries, etc., which I think is in principle of interest to be considered if one really adopts this type of approach. So thank you for your attention.
In the pocket. Can you hear me? Should be good. I put it in the pocket. Okay. Is everybody there? So I was told we were supposed to be exciting controversy and sparking something. And so I'm going to be a little bit different in tone than my good friend Lucien and the other speakers this morning. Because I think, dear friends, I'm very grateful for all of the recognition and the thanks yesterday. But I think with regard to this question, you are not near the solution. And let me explain what I think the question is and what I hear the question being discussed is. So is that okay? Because I know I'm supposed to be sparking controversy, but I don't want to offend anybody. So I start off by saying, of course there is an arrow of time. There is an arrow of time because there is an arrow of time in nature, period. We remember the past and we plan for the future because that's the way the world is. Period. And our job is not to have metaphysical, ontological fantasies like the world should be time symmetric, when it's clearly not, and somehow manipulate them with our very clever mathematics, which you're all much more clever than me about. Our job is to find out what the world is made out of, what the ontology is. And my claim in this short, provocative presentation is that most of us have the ontology wrong. And since we have the ontology wrong, we get the physics wrong. So let's see how that goes. So my title, of course, there's an arrow of time in nature, and quantum mechanics will be, there is the paradox that nature is asymmetric in time, and quantum theory is symmetric. But that feature of quantum mechanics has a very simple explanation. It's because quantum mechanics is based on a certain ontology, which is the same ontology that classical mechanics and general relativity is concerned. Let's see, does the thing, oh, help. It's not, well, I can go ahead. Let me just see if you can fix it, and I'll just go ahead. My claim is that the discussion we could have, and I propose to us, is to compare two ontologies for nature when it comes to time. There is the ontology that Newtonian mechanics is based on, which Roberto Mangabeira and I have called Newtonian ontology. And the basic idea here is that physics is done by having a space of states, which you pre-specify, and an equation of motion on the space of states, which we pre-specify. And the way we do science in this paradigm is we pick an initial state, initial configuration, which is in the space of possible states, and we follow the trajectory set out by the laws of motion for a certain amount of clock time, and then we get to some later configuration, and that's what the theory has done. It has predicted the later configuration from the initial configuration. And we call, again, theories that work that way, the Newtonian paradigm, the Newtonian ontology. And classical mechanics works that way. And by the way, it's obvious that any theory that works that way is time symmetric. And quantum mechanics, the way it was written down by Heisenberg and his friends and Dirac, is structured that way. So we put it in. It's not some deep surprise that quantum mechanics shares in classical mechanics. The fact that it is a little embarrassing with regard to the treatment of time reverse from the fact that nature is time asymmetric. So the discussion we don't want to have, at least I don't want to have, is about fine points of that trouble we've gotten into because we have the wrong ontology. I want to find the right ontology. Let me see if it's in the computer. But let me tell you what I think the right ontology is. The right ontology is based on a notion of time, which I want to call it generative or active. And this is a notion of time where it's not a coordinate, it's an activity. And the activity of time is the continual creation of events. The basic thing that happens in the universe is events. Events are instances where something that was undetermined becomes determined. That's the definition of an event. And we'll see how that matches on to the distinction between the past and the future. And what nature is a continual succession of events. And events, not only that, not only do they, well, an event has predecessors. That is, there are some parent events that give some endowments to the event, to the next event. And these could be energy and momentum and other kinds of charge currents or charges. And so every event has parents from which it was endowed a certain amount of energy, and children, which it passes the energy to. So this is the kind of physical model we're talking about. It's a model of an ontology, which I like to name after Henri Bergson. It's a model we call the causal theory of views. In a minute I'll tell you why. And it's one in which there are no fixed laws, there are no fixed set of states. The system goes about creating the future. And that's what the universe is. Now let me see how much I skipped. Okay, so there are some words about that. But I want to emphasize how different those two ontologies are. And I want to then go ahead and discuss some of the advantages of picking the second ontology as a basis for thinking about quantum theory, space, and time. And by the way, I didn't mention, but I should mention, that my collaborators here include Celia Verde and Marina Cortez and a number of other people down through the years. So how do we build dynamics in this new paradigm? Well, there isn't any distance. There's no space. I forgot to say that. There's a lot of things that could be said, should be said, if you want to devote more than 15 minutes to this. And one of them is that, let me get this in the right order, is that the events pass on to each other energy, bits of energy and bits of momentum. And that's basically where the laws are, such as there are. So, how do we do dynamics? Well, in ordinary Newtonian type physics, there's space, or there are spaces of states. And you can work with motion in space. So you can have trajectories, you can have fields, you can make kinetic energies and potential energies out of derivatives in space and derivatives in time, and we all know how you do that. How are we going to make dynamics in a theory where there's no space? And space is supposed to be maybe emergent later. Well, what we do have is that each of these events has the analog, the discrete analog of a backward light cone. And among the things that are definite are what we call the view of an event. The view of an event is that aspect of the world which is definite and locally associated with an event. And that roughly turns out to be the backward light cone. So let's call that the view. The view is definite, so we're going to call it real. We're going to go for broke, that is, we're not going to be relationalist, even though I'm very often a relationalist. I'm going to be, say simply, I'm going to be a realist. I'm going to say with John Bell that the past views are the be and both in this theory. And the only thing I can do in this theory is compare the past views. So the analog of a derivative is taking two events and comparing what the past looks like, period. So that's what we build dynamics out of. And what do we do with that? Well, I'll go through very quickly what the important results, and there's one more thing or idea I have to tell you about. A lot of people think that this way of thinking goes back to Leibniz. And Leibniz talked about the variety of the world and increasing the variety of the world. So we adopt that. That is, if we can compare any two views of any two events, we can sum over all the pairs. And that gives us a measure of the diversity or complexity of the universe. We call that the variety of the universe. And it's a function you can write down, modulo some simple choices. And so we use that as the potential energy. And so I'm almost at the end. Let's see. So this is, if you want to spend more time on this, there are beautiful uses of variety in biology and computer science, but I'll just skip that. We end up writing down the definition of a theory by a pathway. And that has the kinetic, the potential energy is Q, the variety. The constraints are what keeps momentum and energy conserved. We sum over all the histories consistent with that, and that's the definition of the theory. I just tell you some results, and I'm done. And by the way, there's no H bar, there's no space or space-time. Those emerge, and I can tell you, if you ask how they emerge, but they emerge very beautifully. The theory is fundamentally non-local. If the theory has, as I told you, energy and momentum fundamentally, and it doesn't have space fundamentally, there's no uncertainty principle, so there's no H bar. Those are to be recovered when you study the solution. And the results are that here's the key thing. And this is something that I'm fascinated by. And Carla, we were talking a few days ago, and you discovered this as well, that in quantum mechanics, the function that turns Hamilton-Jacobi theory into quantum mechanics is Bohm's quantum potential. And Bohm's quantum potential, if you take it apart carefully, is a measure of summing over all the pairs of particles in the system, of how much each of them is entangled with the third particle. And that's what the Bohm potential is, and that's what the variety is. So we simply reproduce quantum mechanics in certain approximations, plus corrections, finite computable correction, which I will be happy to talk about. So let me sit down, and we can all be friends again, and I apologize if I spoke too strongly. But I think that for the physics of the future, we have the possibility of discovering what the world is really made of, how the world really works. But there's one obstacle to that. And I say this very sadly because I love quantum foundations and I love thinking about quantum mechanics. But it seems to me we've got to stop thinking about quantum mechanics and stop talking about quantum mechanics and start talking about the physics that may really lie beyond or just after quantum mechanics. Thank you.
Thank you so much, Lee. And our last igniter of discussion is Robert Spekkens. So it's a very Perimeter Institute dominated this session.
Thanks very much. So I'm going to focus my short talk on time symmetry of dynamics, so time reversal symmetry of dynamics. And I'm going to describe a research program for trying to achieve that. And if you don't like the research program, then maybe because you disagree with me on some sort of basic philosophical grounds or some principles. So I'm going to start by just sort of stipulating sort of the background assumptions I'm making here. So the first one is that causal relations are more fundamental than spatiotemporal relations. that we can define space and time in terms of a deeper theory of causal relations. So that means that the question of time reversal symmetry is really a question about causal relations in the theory, and that's the perspective I'm going to take on it here. I'm also going to take the point of view that a sort of purely operational philosophy of science is not adequate. And so in particular, I don't want to define causal dependence as supervening upon operational statistical facts. Okay, so I want causation to be more fundamental. And so basically, I'm looking for realism in quantum theory. And in particular, I'm going to be trying to persuade you that we may be able to come up with a kind of realism that sort of holds on to one aspect of the sort of realism we have in classical theories, which is that statistical correlations do get explained causally. Even though I'm not going to take a purely operational point of view, I am going to take the point of view that the operational phenomenology we see constrains the kinds of realist explanations we should consider as satisfactory. And I'm going to say that the realist theories are plausible only if they satisfy what I like to call the Leibnizian methodological principle, which is an idea that if you've got two ontologically distinct scenarios, but in principle you could not tell them apart no matter what experiment you did, that operationally they were in principle indistinguishable, then you should throw that theory away and start over, so that any ontological differences do have some sort of operational consequence. And hopefully this is something that in quantum gravity, this would be of interest to the quantum gravity people, because in this article I argue that it underlies a lot of Einstein's work, and in particular it motivates the relational program. Okay, and then finally, from my perspective, all probabilities are going to be epistemic and about degrees of belief. Okay, so what's the notion of time symmetry here? It's the standard one that the time reversal of a physically allowed dynamics is also a physically allowed dynamics, right? So this is just the familiar story that, here in Newtonian gravity example, if I take sort of three particles that are evolving forward, and then I imagine taking the time reversal of the final state and evolving that backwards in time, what I end up seeing is also a possible forward time dynamics, right? It's valid according to the theory. So it is the sense in which Newtonian dynamics is time reversal invariant. So I'd say this is the standard notion of time reversal symmetry. And the question is, can we achieve it in quantum theory? And so I want to give a tentative answer to that question of yes, that's what I'm going to try to argue for. But I just want to note that there are also sort of non-standard notions of time reversal symmetry. So there's sort of other ways you might try to achieve a kind of democracy between forward and backward time evolution. So, retrocausation is perhaps one of those ideas. If you have causal influences forward in time, then if a thing is truly time reversal symmetric, there should be causal influences backward in time as well. That goes a bit against the notion that causal relations are more primitive than spatial temporal ones. But we can imagine just saying, okay, retrocausation is the idea that I can't organize my causal relations into some global foliation. Other ideas might be this notion of indefinite causal order, which I'm not going to say much about. And again, the question here is that, are these kinds of notions needed to make sense of quantum theory, or maybe are they implied by quantum theory? And again, I can only give sort of a tentative answer on this, but at least for the case of retrocausation, I want to try to persuade you the answer should be no, if this research program can succeed. So the basics, or maybe the most mature form of this research program is described in this article about unscrambling the omelet of causation and inference in quantum theory. It's with David Schmidt and John Selby. And the idea here is that, to make progress in quantum theory, we got to really figure out what parts of the theory are about our incomplete knowledge, inferences we're making, learn about one system, make inferences about the other, and what parts are really about causal connections. So there's a formalism in this paper, and I'm not going to go into details. I'm going to give you a flavor for it just by looking at an example of what we call a causal inferential theory, and it's just a classical realist theory. Okay, so if I take a classical realist theory, and I'm going to be treating it very abstractly, what does it mean to have a causal inferential theory? Well, it means you've broken it up into two parts. One part is sort of the causal part of it, so the causal theory. And abstractly, the thing that's important for a classical realist theory is that the kinematics is sets, right? So systems, their physical states are basically described by sets, and dynamics is just described by functions on those sets. That's it, just sets and functions. So we sort of formulate this in a category theoretic way, but the basic idea is, kinematics and dynamics is just sets and functions in a classical realist theory. And therefore, for this notion of time reversal symmetry, if your theory posits that the only valid functions are invertible functions, and the inverses of all the functions you allow are themselves part of that set of valid functions, well, then it's going to be time reversal symmetric. And so in particular, if you've got a kind of theory that is symplectic, and so all your functions are just symplectomorphisms on phase spaces, then it's going to be time reversal symmetric. Okay, now the other half of a causal inferential theory is an inferential theory. And so this is about the formalism for describing your incomplete knowledge. So it includes things like, your systems are, again, finite sets. They could be associated with physical systems in the world. But as I draw this horizontally to distinguish it from the causal ones, propagation in this direction means I'm updating my beliefs. So I might start with some probability distribution describing what I believe about W. And then this here is some conditional probability distribution, which tells me what I should believe about Y and Z given W and X. And I might ignore some subsystems, that's marginalization. And there's more to say, but you get this framework for how to do inference. There's a formalism for that, classical Bayesian probability theory. Okay, and a causal inferential theory just puts those two together and allows them to interact. So it allows us to do something like what I've drawn here, that I could draw the causal structure. So in this case, there's some system A, which gets transformed into some system X. And then I stipulate what I know about the value of A, so that's sigma. Here, I stipulate what I know about the function that's being applied to it, if we're in one of these classical realist theories. And then at the end, I might ask questions about X. So pi represents some question I might ask. And there's a formalism for calculating probabilities. But what's nice is that it allows you to do things like, say, I might have correlated knowledge of the value of A and the function that's applied to it, right? I don't have to break things up into chunks. My knowledge could be correlated. I could be asking about a proposition that pertains to lots of different systems at different times in this causal sequence. Okay, there's a bunch of axioms that characterize how these sorts of diagrammatic elements are going to interact. But I want to just make a few points about time symmetry. So the formalism allows you to make inferences from early times to late times. So I might start out knowing something about this system and be interested in answering a question about a later version of the system. Or I might start out knowing something about the later version of the system and try to make inferences about an earlier version. I might see some fossils and want to update my probability that the dinosaurs existed in the past. So the inferential theory interacting with the causal theory allows you to do both of those things. And so now imagine this proposal that we have a notion of inferential time symmetry, which I'm going to try to make sort of parallel to the causal one I had earlier. The idea would be this, that if you give me a valid forward in time chain of inferences, then the backward in time chain of Bayesian inversions of each of those inferences is also a valid forward in time chain of inferences. So it just sort of says, oh yeah, if I update my knowledge backward in time, and then I flip it over and say, well, is that the kind of update of knowledge I could have had forward in time? If the answer is yes, I say, all right, well, that has inferential time symmetry. So the question is, if you find a theory that satisfies that, does it imply that it has this causal notion of time symmetry? And I want to try to persuade you that it doesn't, right? So that having this inferential time symmetry is not sufficient for concluding that the fundamental dynamics is time symmetric. Okay, so it's a bit of an artificial example, but it makes the point. So the idea is, imagine just a simple dynamics from one binary system to another, x to y. For two binary systems, there's only 4 functions. There's the identity, the flip, and the function that makes the output 0 regardless of the value of the input, and the function that makes the output 1 regardless of the input, which are these reset to 0 and reset to 1 functions up here. Okay, so now imagine these two different states of knowledge. In one, you're ignorant of whether it's identity or flip, and you assign equal probability to the two. And note that both of those functions are invertible. They're the kinds of things that, if I take their inverse, if I have a theory that say the identity function and the flip function are valid evolutions, then their inverses are valid evolutions as well, because their inverses are equal to them. But over here on the right, I have a state of knowledge where it's probability half reset to 0, probability half reset to 1. Those functions are many to 1. They're not invertible. If I had a fundamental theory that said, sometimes this is the function, that's not going to have time reversal symmetry because I can't invert those functions. But if I look at the conditional probability that these two states of knowledge define, it's exactly the same. The conditional probability of y given x on the left is just the sum of these two stochastic matrices, which is this one, oops, and on the right, it's the sum of these two stochastic matrices, which is the same thing. So the conditional probability just says whatever the input was, whatever the distribution of the input was, generate the uniform distribution on the output. But it can arise through either of these types of ignorance. So what that means is if I have a theory where I just tell you what the valid conditional probabilities are, let's say it's only the completely randomizing map, and then I say, all right, well, what's the Bayesian inversion of that for, say, a uniform prior in X? Oh, it's also the completely randomizing map. Oh, great, I've got inferential time symmetry. But it doesn't tell me whether it arose from the left-hand or the right-hand option. In one case, the fundamental dynamics is time reversal symmetric, the identity and flip case. In the other case, it's not time reversal symmetric. So just looking at the fact that I have this inferential time symmetry cannot justify the claim that the underlying causal dynamics is time symmetric as well. Okay, so let me move on now to the claim that we can achieve realism and satisfactory causal explanations of correlations in quantum theory, and therefore sort of have a time reversal symmetric version of it. So the challenge to doing that is Bell's theorem, right? So I described for you a classical realist causal inferential theory where causation and inference are cleanly distinguished. Unfortunately, that sort of picture cannot underlie quantum theory. That's one way of thinking about Bell's theorem. And so in the language of our framework, this is what a Bell experiment looks like. You've got some common cause that you have some knowledge about, and then you've got measurements on the two wings. These are the settings, S and T, the outcomes, X and Y. And I'm going to just, there's a sort of a map that takes this kind of structure to a directed acyclic graph and what's called a classical causal model. You can sort of infer from what you know about these things what these conditional probabilities are. So this is the conditional probability of the outcome on the left given the setting and the hidden variable. You can compute the joint probability over X and Y given S and T and prove that that satisfies the Bell inequalities. Quantum mechanics violates those. So this sort of picture of what's going on doesn't work. It can't explain the correlation. So you can, if you like, stick to that classical realist framework. So I guess I shouldn't have said you can't make it work. You can, but you have to go with a causal structure that's not the natural one. So if you allow that, for example, the setting on the left can influence the outcome on the right, if you hypothesize that that's the deeper causal structure underlying the experiment, never mind the fact that it doesn't really look like that in the lab, but if you say that's what's really going on, then your classical causal model looks like this. There's an extra arrow. Now Y can depend on S. I got this extra term here, and now I find I can violate the Bell inequality. So I can do justice to what I've seen, but there's some problems here. So one is, you might think relativity, if you take the point of view I'm taking, you might think that relativity doesn't merely imply that signals can't go faster than the speed of light. You might think that it entails that causal influences should not go faster than the speed of light. So if the Bell experiment has been done at space-like separation, this model is basically positing causal influences that are going faster than the speed of light. So in that sense, it's in tension with relativity. But furthermore, to explain the no signaling, you've got to choose these parameters very carefully, because in general, this sort of model could describe signaling. Now, let me note, I mentioned retrocausation at the beginning. Let me note that from this causal perspective, having these sort of zigzag pattern of influences where something goes back and influences something backward in time and then something forward in time, that's actually no different from having causal influences that go between the wings of the experiment. So endorsing retrocausation doesn't give you anything more than endorsing these interlab influences. So if you can give reasons for not liking this sort of causal model, you also have reasons for not liking the retrocausal model. So the big idea here is that there's another possibility that we can reject this classical realist causal inferential theory and instead try to define a realist causal inferential theory that's somehow intrinsically quantum. So what do I mean by that? Well, it's going to be the same kind of abstract structure, but now instead of sets and functions, I have something different. So it could be operator algebras are the systems, and unitaries are playing the roles of functions. So the way these things interact, the sorts of rewrite rules I have are going to be different in this case. So this is described in this paper and other papers that Ognyan was referring to in his talk. And because you know the inverse of a unitary is also a valid unitary, if you can make this work, then you have a notion of time reversal symmetry. But you also need an inferential theory, and so the idea here is that we can have an intrinsically quantum theory of inference as well. And there's been a lot of work done on this, and the idea is that, again, you know, rather than sets, we have something like algebras, and now instead of probability distributions, we have density operators. Instead of these conditional probabilities, we have what Matt Leifer and I called conditional density operators. They're basically just isomorphic to completely positive trace-preserving maps. Instead of marginalization, you have trace, and so on. So the idea here is that quantum theory involves an innovation not just on the causal side, but on the inferential side as well. And then you can say, all right, well, let's try to explain what we see in a Bell experiment. So you go from this sort of picture where now these elements mean something different. I don't have sets and functions anymore. I don't have probability distributions describing my knowledge, but these more exotic sorts of elements. And that there's a map to what's called a quantum causal model, where instead of these conditional probabilities here, I now have these conditional density operators. And you know, I haven't told you the details about that, but there's a sort of formalism that allows you to combine these things in a way that's very similar to how you would use conditional probabilities to compute the statistics you would see in this experiment. And what you find is that you can violate the Bell inequalities and get exactly the quantum bound with this sort of model. So one way of thinking about this is, where do you want the radicalness of quantum theory to be? On the left, you've got a radical structure. You know, this arrow that goes across. On the right, things are conservative. But on the left, you're conservative about what the causal theory and the inferential theory look like. It's just sets, functions, you know, good old Bayesian probability theory. On the right, that's where things go radical. It's something more abstract than that. So, you know, we can talk about those differences. I have a number of arguments as to why you ought to prefer the thing on the right. I sort of mentioned harmony with relativity. In recent work, we've shown that only the thing on the right can preserve this Leibnizian principle. And then there's another sense in which the thing on the left overfits certain experimental data. Let me just conclude. I describe this as a research program because the story is not finished. We haven't really got a set of axioms to characterize this intrinsically quantum realist causal inferential theory. There's been a lot of work on quantum causal models. I've listed some of those references here. And we're trying to sort of fit those things together. And my view is that there's sort of still some more unscrambling of the omelet that has to be done. In particular, I mentioned before that a conditional probability distribution can be understood in these two different ways. Very different interpretations of what's going on causally. In the past, we've been focused mostly on the quantum analog of those conditional probabilities. But what we really need to focus on to unscramble the omelet is what's the quantum analog of this probability distribution over functions. That's what's still unclear. Okay, so let me just end by saying, even if you disagree with me, I think the kind of question, you know, what is the right causal explanation of Bell inequality violations is really critical, because if we do want to unify quantum theory with relativity, given that general relativity, you know, causal structure is so important, if we can't know what the right causal explanation of even something as simple as a Bell experiment is, then, you know, we shouldn't be surprised that we might have challenges understanding how to unify quantum theory with GR. I'll end there. Thanks.
Thank you. So it's time to take a break. And that will be a bit shorter, just 20 minutes, 50 minutes, and then we can